opportunity. So I think there was a wide range of different presentations and topics over those 3 days, and we would like to give a presentation that gives a little bit more a spin on the simulation topics and what can be done in autonomous vehicles on that front. Just to put the scene a little bit and set the scene a little bit. I mean, simulation is around for many years, decades almost. Started with basic FEA, most common for that. But then we have also things like temperatures added, for example, to look at welding processes and then look at deformations and so on. On the FEA and on the structural side, of course, a very modern topic at the moment is 3D printing and topology optimization. So we have a load case for a certain body, and then we can, or the optimizer is taking elements in and elements out depending on where the stresses are, and then we come up with that organic structure and can then print it. And we can even then forecast the printing process and look at what the structure does, how it deforms to just reduce wastage. One step further is electronic pre-compliance. That is a big topic in Australia at the moment because we can reduce the amount of testing in anechoic chambers significantly. So it's a bit more complicated because you have to often connect 2D circuits with loads and excitations to the 3D world. The 3D world always then takes over the coupling of the fields in different lights and so on. And then the latest technologies and also ideas. One is digital twins, where we connect simulation models to sensors in the real world, taking that as an input and calculating new properties and field qualities to then make a forecast or changing our model in the field later on or in real time. The second aspect is digital missions engineering, a big topic at the moment, especially in the defense world, really simulating systems of systems where we we combine geographics and terrain with, for example, the kinematics of a mission of a drone, the flight characteristics of a satellite constellations and so on, to find out what is the best way to go through a mission and to plan that. So why are we doing all that? Very quick, I think most of you guys understand what is the background of simulation. It's basically to shorten the development time. So we don't want to build a physical prototype all the time, test it, and then find out if it failed. What we want to do is build a digital prototype first, run it, analyze it, optimize. It's a big topic, and we can do that very quickly. And then building a physical prototype that then passes the test immediately. So that's the idea about it, and to shorten the simulation time and the manpower needed to get to new products. What do we need to have that for autonomous vehicles? And I would like to put your attention to the open loop, which is basically looking at the components itself and then having inputs and calculating the outputs, but then also we can run everything in the closed loop, where we have our environment, the motion, and also the sensor models and the rate of radar, camera, and LiDAR, all connected, linked up with software, and then combined with the vehicle dynamics. So you can see there is a loop set up, and tools and different objects are talking to each other. A very important aspect is also the functional safety that we can cover and should be covering in the same environment. And that's where you really put a lot of miles in to test everything, and you can see that there are tens of millions of kilometers per day, but we can capture that in scenario-based validations. That is mostly 1D, 2D, but it helps us a lot to get edge cases. The second aspect is the performance testing. That is really where we're using hardware in the loop and also the closed loop simulations that I discussed just now. And then, of course, something we can't do in simulation that has to be on the road is then the real drive testing. But that then narrows it down to a lot less kilometers and a lot less time, hopefully. I would like to start with camera. There are a couple of edge cases and difficult cases where we say you cannot really just take a picture and feed it and merge it with your software and then make decisions based on that picture. You really need a physical approach to capture all those different lighting effects in your scenarios. And there's, for example, the reflections. There is low exposure. You can see the person. It's very difficult to see. In an ideal picture, it would be probably easier. And then you have blooming, which is like a supernova of light sources in a dark background that can happen. And then also the effect of sunlight. Other things like droplets on a windscreen, very important, where the camera effect actually degrades the visibility further, and then of course makes it harder for the algorithm to detect all those things. So camera simulation, yes, we can do the full lens stack up and the component, but what is more important probably for the autonomous simulation and vehicle aspect is that we can take the camera and put it on a dashboard, for example. The dashboard and the car are a model that looks at the ray tracing with a ray tracing engine, and we can load in a picture like the park spot here, the park lot, and merge it with the simulation tools, merge it with the simulation results. So the spot in the lower end of the picture, the dashboard, is completely simulated, and the picture is then put into it, plus the camera is added to it. So we're producing real-world pictures based on real camera performance specifications. For example, depth of field, distortion, and all those other things like looking at different resolutions. How does it work? We can take a scenario and simulate the full scenario with different material properties. We can bring natural light in, we can look at the geolocation of things, and then what day is it, and then it tells you where the sun is sitting. Artificial light like LEDs and also traffic lights. Then we can put in, or we have to put in the spectral domain of characteristics of the material properties. The camera model, there are different camera models, for example, or sensors, like pinhole cameras and iridium sensors that you have to underlay. And then you can come up with a pixel grid, which is good to compare to standards, compare the results to standards, or a raw view and even perceived view, which is then the rendered result. LiDAR is very similar from the component to the driving scenario. Again, it is very important to know where you put your LiDAR system. Often it goes into the headlights, which is degrading the performance further of that. You can test that based on your vehicle. I put that slide in because we had a conversation on our booth the other day. Do we have LiDAR models as well if you don't have a component from a vendor? Yes, we also have that, so you can test different LiDAR systems with a certain beat pattern and the firing sequence directly in the software as well, without knowing too much about the details of the component. So that is how it looks like. So we have a vehicle traffic scenario set up. The vehicle passes by, crosses a couple of roads. The LiDAR is in real time running next to it, together with the software. And the software then can make either detect what's happening on the scan, and then also make decisions further on. And you will see now there is a pedestrian hitting the road, and of course the software then can make the decision to stop that vehicle. So that is, for example, a good example of an open, of a closed loop simulation. We also have the solution for the radars. Radars can be simulated as well and should be, especially for those cases. For example, the rail guard effect, where you have really ghosting on the side, so you cannot, with the rail guards and the reflections happening there, you cannot really detect a person on a bicycle or a person walking next to it. So that is an area where we would want to have a physics-based Doppler range radar built. And then also bounces and tunnels, reflections on holes on the road, and then also ground reflections and so on. The implementation of radar systems is very important because it can also, like the LiDAR, degrade the quality of what we will receive in terms of the scans and the Doppler range. You can see that here, for example, just operating the radar in open space and operating the radar completely integrated in the vehicle makes a big difference in terms of the errors we get. That's a good example here. So very short wavelengths, it sees all the details in the environment. So it's important to integrate into the vehicle and then also look at what the shape is and the material composition of it. And then also variations, how to mount this thing. So those things should be covered. Here's an example where we integrated it directly in one of those car bumpers in different angles, phi and theta, giving the result. You can see there are differences between the open and free space simulation where we just have the radar system and the radar mounted on our vehicle. Here's a traffic scenario. A radar simulation where we basically set up all moving vehicles as coordinate systems and variables, and then we plot that Doppler range profile. The simulation is a frequency domain simulation. You have to do a couple of steps to do that, but the post-processing and the plot of that Doppler range is automatically received with a couple of steps that are happening under the hood. To just show that how accurate that simulation can be, is we have different roughnesses of road and asphalt, and we can also take that into account. So you can see it makes a difference if you have a rough road or if you have a very, very glass type road. So there can be a difference, and the simulation will pick that up as well, and then be able to provide that picture or that plot to the software. That's one of my last slides. The entire approach can be wrapped into a platform that lets you train and lets your software to learn. And the radar is so fast, the simulation is so fast that it runs in real time, and also with certain ways of using more cores and also GPUs. And in that case here, the car is moving through the traffic, and every time it does an accident, it gets a negative reward here. So you can see that across a number of episodes. And the car is then controlled by the throttle, the software is controlling the throttle. So, and that's the last slide. That is to give you an idea on if you are an OEM or if you are a tier 1 or tier 2 supplier where you don't really have the algorithm and the detection, the perception algorithm on your yourself. It's mostly given on hardware and semiconductors. So you can, with the hardware in the loop scenario, bring in your plant where the detection algorithm is sitting on the ECU and so on, and then connecting everything to a real-time simulation. So we have the wrapper for the driving simulator where we set the scene for that. We have the GPU-based AVX cluster that runs the camera and the radar analysis. And then, of course, the instances that pass everything on, and the vehicle dynamics for everything, and the rest was simulation, which is not covered by either the hardware or the simulation. So I would say there's a lot of things happening, a lot of opportunities to really be faster in terms of development for autonomous, and I think we have given a little bit of an overview and an insight